Hello, Derek. Can you hear me?
Oh, yeah, I can hear you.
Hi, wonderful. Right. So, okay, Derek. So welcome. Derek, can you, so we have an hour and a half for the class.
Yep.
So if you don't mind, just leave me some like 10 minutes, I can close the class. So you can spend like 120 minutes. How's that?
Okay, that sounds good.
Okay, yeah. Wonderful. All right, so yeah, it's 7 o'clock now. So today, we will introduce a new topic. Well, actually, it's not a new topic. We will focus on one thing that we have been doing this. However, we haven't paid a special attention on that, which is the algorithms, right? What is the algorithm? Algorithms refer to a set of instructions for problem solving. So when we solve a problem, how we can solve it in a good way, in an efficient way, and especially we can overcome some time and space limits, right? So today we have a guest speaker, Derek Chin. Derek Chin is let me introduce him. Derek Chin. Derek is a sophomore at CalTech, studying computer science and information data sciences. He has a lot of experience in machine learning, computer vision, and artificial intelligence. At high school, he was the salutatorian of the Plano West Senior High School, which is one of the most famous public schools in the United States. He was the co-founder and the vice president of the Association for Young Scientists and Innovators, which gathered a group of most innovative young men in the United States. He's currently a machine learning researcher at CalTech. He plans to go to industry as a software engineer in the summer. Okay, so without further ado, let's invite Derek.
Yeah, thank you for the introduction, Dr. Ming. I'm really excited to teach you guys a little bit about kind of algorithmic programming and introduce you guys to user code. So yeah, do you have a little bit of like a few slides before, or do you want me to just jump into like what I wanted to?
Yeah, I can. Yeah, you can share your screen.
Okay. Yeah, so can everyone see kind of
yes
the setup?
I can't see your screen sharing thing.
Okay, now I can see
mine.
that.
Now I can.
Okay, so there should be like a Chrome tab and like, yeah. Okay, let me pull this up. Okay, so yeah, so you guys have been learning a little bit of programming or software development using App Inventor, and I'm going to introduce you to a little bit about the other side of, or kind of a different side of programming that a lot of young students like to get into, which is competitive programming. And so what is, so competitive programming there's the gist of competitive programming is solving problems with limited time and limited space. So what does space mean? Space means like computer memory is the main use of space. So let's say I can only store however much information about this problem, and that's my limit on space. And then time would be how I only have so much time to solve this problem. Yeah, and so this kind of leads to programming contests, competitive programming contests, where the program organizer, kind of like math contests, you'll have someone who organizes it and writes the problems for you. They'll provide like sample test data, and your task will be to write a program that takes in the input and spits out the right answer within these time and space constraints. And so one of the most popular contests, or like the most popular feeder system for these contests in the United States is USICO, which is the USA Computing Olympiad. And this is kind of like your it's the same as your Math Olympiad Math Olympiad style contest. There's feeder systems, everyone participates, and you eventually get selected to international contest, which is the IOI. It's kind of like the IMO for math, but this is for coding. This is the International Olympiad in Informatics. And these are all kind of the same kind of programming problem solving contests. So for USICO, there's 4 divisions. There's platinum, gold, silver, and bronze. And these 4 divisions are the ones that you kind of move up through. So this would be, you start from bronze and you move up to platinum. When you get started in bronze, this is kind of very basic programming knowledge, and like very basic understanding of algorithms. For silver, once you get to silver, you kind of have an assumed programming knowledge, and this is more advanced algorithm. Well, not advanced per se, let's say intermediate. And then gold would be something advanced algorithms. And once you get to platinum, this is very math. This is like a very much a combination between math and algorithms. So these are kind of the tiers. And once you go up to platinum, you enter the team selection for the IOI. And these are kind of the tiers. Each year they'll hold several contests where you can promote through these tiers. So let's say there's like a winter or like a February contest, then there will be a set of problems for each 4 of these tiers. And if you manage to solve the problems in one of the tiers, or solve it enough, and you get a high enough score, you'll get promoted to the next tier. And so, for example, in the February contest, if I do well on the bronze set of problems, then I can move up to solving the silver set, and then after that, the gold and platinum, and so on. Yeah, so yeah, you get promoted through these divisions, and then you eventually get up to the international level. Now this contest is usually these contest tiers are more traditional programming languages. So written languages like Java, Python, or C++ are very popular to be used for these. But since you guys are mostly still learning how to think programmatically, we'll be using today's demo. I'll be solving a problem from USICO Bronze, and we'll be using App Inventor just so you guys can get a feeling for how the algorithmic thinking works, and not have to worry about language syntax and things like that. Okay, so does anyone have any questions before I introduce the problem? Okay. Yeah, so the problem we're going to be solving today, this is the problem statement. This is actually from the 2021 February contest in the bronze division. And first, we'll just read through the problem. I'll just read it out loud and kind of highlight different points. So Farmer John's cows are excited to learn that Chinese New Year was recently celebrated, ushering in the year of the ox, always a bovine favorite. As we know, the zodiac animals for Chinese calendar years follow a 12-year cycle. So this is a cycle: ox, tiger, rabbit, dragon, snake, horse, goat, monkey, rooster, dog, pig, rat, and then ox again. So Bessie the cow is proud to say she is born in a year of the ox many years ago. Her friend Elsie wants to know how many years apart from Bessie she is born and hopes you can help her deduce this by looking at relationships between the birth years of several cows on the farm. So the input format is this usually will come in on a terminal, which is kind of how most commonly you run programs. But since this is, we're going to be using App Inventor, we'll put the input in like a text input box. Okay, the first line of input contains an integer n, one less than 100, between 1 and 100, and each of the next n lines contain an 8-word phrase specifying the relationship between the birth years of two cows. Okay, so if we look at the sample input, this is the number n. It'll just be the first line. It'll be the number, and then after that we have 4 lines of input, or 4 lines of phrases, which are what it describes next. So what these lines are like: Mildred born in previous dragon year from Bessie, or Mildred born in next dragon year from Bessie. These are 2 examples, and it's telling us what these phrases are, what kind of the restrictions on these phrases are. So it says first that the last word is the name of a cow on the farm, which is either Bessie or a cow that has already been mentioned in a previous line of input. So if we look at this, the sample input, the first line contains Bessie. So this is telling us Mildred with respect to Bessie. And then the next line, the cow that it's in the last word is Mildred, which has been previously mentioned up here. And the rest of these cow names, Greta and Bessie, have been mentioned before the line is written. So what basically means what won't happen is we'll have a line that starts with Elsie, and then Elsie is mentioned, up here. But it's one of the rules is that this will always come after this. Okay, so the first word is the name of a cow on the farm who is not Bessie and who has not yet been mentioned in the input. So this means that when the cow is mentioned in the first word, that means it's already been mentioned before, so we can kind of infer from above what the cow's birth year is. And then all cow names have at most 10 characters that are in the range A to Z or capital A to Z. So this restriction we shouldn't worry about too much, but basically this will make it so that you can store these kind of without having to worry about super long strings and things like that. The 5th word is one of the 12 zodiac animals above. So we have 1, 2, 3, 4, 5. So this is the 5th word. So the 5th word is always dragon or monkey or ox or dog. Those are in the examples. And then the 4th word is either previous or next. For example, if the phrase is Mildred born in previous dragon year from Bessie, then Mildred's year of birth was the dragon year closest to and strictly before, not equal to, Bessie's birth year. So that's pretty self-explanatory. It's the next year that is cowrized dragon. Then the output format. What we want is to output the number of years by which Bessie and Elsie's birth years differ. So it's guaranteed that this number can be determined by the input given. So this is just, we want specifically 2 cows, Bessie and Elsie, and we can guarantee that they're mentioned somewhere or Elsie is mentioned somewhere. And we want to see um, how far apart their birth years are. Okay. Hey, does anyone have any questions about the problem? Oh, okay, so I'm going to go into how we're going to approach this. Right. Right. So first off, one of the things that we get is the list of the zodiac animals, right? And we know that they're going to cycle through those, and we're gonna go through those. So let me just write these down. Tiger. Okay. So this is kind of the cycle. And we know that, for example, if this one is 2021, then 2022 is this one, 2023 is this one, and so on. And we can keep filling this in until we get back to ox, which will loop around after rat, and this will be 2030. So they're separated by 12 years, and there's an infinite number of years that are ox years. They're separated by 12, and there's that many years in tiger years, and so on. And they repeat in a cycle. Okay, so this is kind of how we have to look at it. And then now let's see how we're going to parse the input and actually solve the problem. So one of the good things about this problem is that it's guaranteed that the next cow that we're looking for is based in relation on something from one of the previous cows. So for example, if we have Mildred, if we have Mildred here, and this is in previous dragon year from Bessie, we can go up here and we can say, okay, Bessie is here, 2021. Then we can count backwards. We go from ox to rat, and then count backwards and backwards until we get to the last dragon year, which would be here. So if Bessie is 2021, we can keep going backwards to like 2020 and check if this is a dragon year. This is a rat year. And then 2019, this is pig. And we can keep going until we get down to dragon, which would be 2012. And then once we figure this out, we know that this Mildred is 2012, and we can store that, or we can keep track of that somehow. And once we know that Mildred is 2012, let's look at the next sentence. Let's say if the next example is Greta. In previous monkey year from Mildred. So if we know Mildred is 2012, then we can look at Greta, or we can go to 2012, which is a dragon year, and we can go find the previous monkey year and count down until we get to the last monkey year, and so on. And we can do this with the next sentence for Elsie and Paulina as well. Okay. Once we do that, once we figured out Greta from that, we can then figure out Elsie. And then in order to produce our answer, we can just subtract Elsie's year minus 2021. And then we can compute how far away those two, how far away the years in between those two cows. Okay. And so now let's start putting in a little bit of like kind of programming sense of what we would need to do in order to figure this out. So what information did we need in this previous or like kind of writing out how we would solve this problem? Well, one piece of information that we needed was the sequence of animals. So if we're writing this in programming, like we need some way to, in order to map these animals onto years. And we want to do it in a way such that we can capture all of those numbers, like every single one of those years, without having to store every single number. Like I don't want to have a list of, let's say, ox years, and I have to store 2021 and 2033 and 2045 and all of these numbers. I just want to be able to store very basically, or like in as little information as possible, all the years that are ox years and all the years that are tiger years, and put that in a very short function. So in order to do that, I'm going to introduce something called the Modulo function, which is, it sounds a little complicated, but it's very simple. This is basically the remainder after dividing by something. Now, it's not really a function per se, but more of a kind of working environment. Now, how does that work? When you're working in the modulus of like under some sort of modular arithmetic, basically every number is equivalent to its remainder divided by the base of that modulus. So now, first of all, let's determine what modulus we want to, what number we want to divide by and find the remainder of in order to compute all these years. And it's pretty easy to see that if you have a 12-year cycle, if you cycle back every 12 years, then each time you cycle back and you divide by 12, the remainder will be the same. So like, for example, 2021, or like if I cycle back, if I have like, okay, actually, never mind. So if I have, let's say the ox year be 0, and I go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then I'll come back to ox year. The ox year, it will be 12, right? And the next one will be 13. And if I look at the remainder when I divide 0 and 12 by 12, they're both 0. And same if I divide 1 and 13 by 12, the remainder is 1 for both of them. So if I operate in this is how you kind of write it. And this like kind of funny equal sign, which is 3 lines, which is read as congruent to 0 and 12 are congruent to each other modulo 12, which in other words is saying 0 and 12 have the same remainder when divided by 12. And this is also true for 24 and so on. And so now if I look back at these animals, or these animal names, I can basically sort each one into a modulo, like into a modulo class. And the way we pick these can be kind of arbitrary, but we can just say 0, 1, 2, 3. Right. So I'm just going to say if I have a year and I divide by 12 and its remainder is 0, then let's call that an ox year. And if I have a year and I divide it by 12, the year number by 12, and I get a remainder of 1, we'll call that a tiger year, and so on. And so that's how we're going to define, we can define our all of the zodiac years. And so if we're writing a program to do this, we need some way to store that. And the easiest way is we're looking at some text data and some number data, and we're going to want to compute the number based on the text, because the text is going to be in the input and we want to match it onto the number. So our first data structure that we're going to need is some sort of dictionary mapping animal name to year module, right? So this is going to be one of the first data structure that we need. Okay, so going through our steps for how we were going to figure out all these years, there's another thing that we needed, the information that we stored was this information and this information that we stored under these 2 cow names, right? And so the next piece of information that would be helpful for us to store is for each cow, I want to store the birth year. And that way, every time I figure out a new cow, I can store its information. And then when I look at the next few sentences, I can just pull the information on what year this previous cow was born in, and then use that information to compute the next cow. Okay. All right, so those are like the 2 kind of, those are like the 2 big pieces of data that we're going to need to store. And then next, we can figure out kind of how we're going to write a program around this in order to solve the problem. Okay, so in general, or like looking at how I outlined this problem solving algorithm, we're reading in the lines of input and we're using each line to compute the next line. So the very first thing, if we kind of write out what steps our program would do. So first we initialize so this is our dictionaries and other things that we'll need in order to store all the data that we have. That's the first step. Then second, you want to read the input, right? So we want to take in this paragraph of text and split it up into sentences. So reading input. So we want to read each line, right? or you want to split it up into lines. And then we want to split each line so this way each word, like the words that we want to know, like the name of the next cow, the year of the animal sign of the year, and the name of the last cow, and then also whether it's the previous or next. Okay. And then after we read the input, then we can, then how do we write in a program, or like how do we solve this thing? So we want to read each line, you go line by line. So for each line of input, what are we going to do? So there's two cases that can happen between each cow. One of them is if it's the previous year or if it's the next year. So if it's the previous one, how are we going to find the previous such and such year from some year that we already know? Well, we can just take the last cow's year. So we can take the last cow's year. And we can keep subtracting from that. And then keep subtracting until right animal. Wait, does that make sense to everyone? Oh. There's chat activity that I didn't see, sorry. Okay, never mind. If you want to get my attention, just unmute and then. Yeah. Okay, so then if it's the next one, we can do kind of the same logic. But instead of subtracting, we can just keep adding. Okay, so doing this, since we're doing for each line of input, this should be able to calculate, or this should be able to compute every cow's age or every cow's birth year based on those inputs, because we're guaranteed in the problem statement that each cow's thing will be on there. Okay, so yeah, so last cow, we're just going to say this is the last cow in the sentence, basically. Since each sentence is saying we're going to give this next cow is going to be, for example, Mildred, born in previous dragon year from Bessie. This we're going to compute the next cow's year that we're going to compute is Mildred, and they'll based on the one that we know, which is Bessie. So that's going to be the last one, and then the next one is going to be Mildred, the next, which is the next cow's year that we're going to compute. Okay. So after we've done that, well, what answer do we want to give? Please output is please output the number of years by which Bessie and Elsie's birth years differ. So we've calculated every cow's birth year in this big loop. So then the last thing that we need to do in order to get the output is print out the birth year of Bessie's, the difference between Bessie's year minus Elsie's year. And since this is not necessarily positive, we want to take the absolute value of this, and this will give us the difference or the number of years between those 2 years. Okay. Does anyone have any questions about this kind of algorithm? Okay, so if we've done that, I can now get started on how to solve this. Okay, so now I'm going to start writing it up. So this is kind of my App Inventor setup right now. And we can figure out the layout very quickly and kind of just move on to the backbone of it, which is the code. So what we need is some way to get the input. So I'm going to make a text box and some way to tell our app to compute the answer, which we're going to use let's just use a button. And we need some way to print out the output. So we can just do some label here. Can make the height. Let's make this as big as possible, because the text is going to be big. And yeah, if you guys want to follow along and want me to slow down, just tell me. But otherwise, I'm going to just kind of move. Okay, so this box also needs to be multi-line because we have, if you look at the input, it's multiple lines, and we will want to split these lines. And we can make this just slightly cleaner so we know what is what. Let's just say this is input box. Let's just say this is solve button. And let's just say this is output. Okay, so those are our things. We don't really need to do anything else. We can move directly on to the code, I think. Yeah, so the very first step that we needed to do is to initialize the data structures that we're going to use to solve the problem. And so the very first one that we need to predefine, because that's like part of the problem statement, is a dictionary of all of the years for each cow. And so I'm going to make these global variables so that they can be accessed everywhere. And so this will be like this. And so we're just making a big dictionary. Hopefully I have the right number of these. One, two, three, 4, 10, 11, 12. These, delete all of these. Right. Okay, and then now we need to fill in how we predefined these. So since this doesn't really particularly matter, we can just go down the order, ox, and we'll say this is 0, tiger. We'll say this is 1, rabbit. We'll say this is 2, dragon. We'll say this is 3, snake. So this is 4, 8, 6, monkey, 7, 8, 9, 10. So this will be kind of our pre-definition, and we'll just say this is makes it a little easier for us to remember what this is for. Okay. All right. And then another thing, the other thing that we need is a dictionary to contain the age of every single, or the birth year of every single cow. And so at the very beginning of each problem, we only know one, which is, or we only know the age for one of them, which is Bessie. And all we know is that Bessie is in the year of the ox. So besides that, we don't really know anything else. So for simplicity, we can just say Bessie is born in year 0. Now, why can't we choose 0? Because each year, it doesn't really matter what year this number is, as long as number 1, it matches up with the modulo for ox, which is 0. When you divide 0 by 12, you get a remainder of 0. So that's how you get this. That's how you can get the correct classification for Bessie's year. And then the other one, since we're looking for the difference between Bessie and some other cow's year, they will all kind of sort itself out if you start from 0. We're looking for the difference, not like the actual number year. Now, if it was the actual number year, if the question asked for, if the question gave, let's say Bessie was born in 2021, and the question answer asked for what year was Elsie born in, then you would need to set this correctly, or like set this to exactly 2021. But in this case, you don't need to. So let's just say this would be cow. This would be our dictionary in order to store exactly when each cow was born. Okay. Next, Another thing that I would like to have is a list for the input. Now, why do we need this? It's easier to access. It's sometimes easier to access the input and like modify this input list and just store all of our input data into this list instead. And so we're going to create an empty list because right now there's nothing in the list. Just that's that's how we'll initialize that. Okay, now we can set up kind of the basic framework before we move on to the actual algorithm that we use to solve it. The first is what will happen when we hit solve. So solve, when we hit solve. So something that's happened in this is, or the way I've set this up, is that, well, animal dictionary will never change because these will always stay the same. But if I change these, the input and the cow born years later, they'll change it. Or like if I solve one version of it and I add stuff into this in order to solve the problem, then eventually if I try and solve something else, it'll just keep adding onto this and not reset it. So one thing that we'll just do here is to set these things back to their original values. This is just usually not necessary in these kind of things, but the way this program works. Okay. Then we'll write some function. We'll write two functions actually. One of them will say read input. And then another one we'll say is to actually solve the problem. Right, so these two will be later. And so what we'll need to do is call the input. We'll read the input here, and then we'll print out our answer, which will go in this output label. And also we'll set the text to this. Okay. So what should happen is we'll read the input and then we'll print this out. Okay. So how do we read the input? Well, the input is given to us as kind of this paragraph. It's multiple lines, and usually with other kind of other programming languages, the reason this number is included or needed to be included is because other programs won't. Some languages won't be able to tell when this terminates. So it will just keep reading nothing, and it won't be able to tell that it's reached the end of the input. So that's why for some languages you'll have this for is necessary, because that way you know to read 4 of the next lines. But since we're doing this just in one text box, it will know exactly what the input is and when it ends. We won't particularly need this for. We'll just need to split these sentences up and get the right input array. Okay, so and then the other thing is, once we split this up into sentences, we'll also want to split each sentence into words. So what it will look like is, we'll have like a list of sentences, and then in here will be all the words. So this will be like Mildred. I don't remember what the other parts of the sentence were, but this will go all the way to the end, all the words in the sentence. And then our next item in the list will be the next cow, the next. And then this will be Mildred at the end, and it'll keep going, and we'll have the end of the list. And so what this will let us do is go through each list at a time. We'll go through this one, and then we'll be able to select which words we want from this list. That makes sense to everyone?
Yes. I got a question.
Okay, yeah, go ahead.
Can you speak up a little bit?
Okay. I can adjust the volume, I think. Does that sound better?
Yeah.
Okay. Cool. Yeah, I just raised the sensitivity on my mic a little bit. Okay. So once we've gotten this list, then we'll be able to read the different words from this. And so yeah, we'll go back to this. And so how do we read the input like that for this problem? So it'll be given to us in this paragraph, and we need a way to split this paragraph into the separate lines. Turns out, or if we're looking at our text functions, we can see a few things, or two of these split functions, and this is the one that we're going to want. And the way you split lines, in one of the standard convention for writing lines of text is there are things called escape characters that kind of are invisible to you, but your computer will see them. That tells your computer this is a new line, happens here, or a tab happens here, or different things like that. This escape characters can also be used to read things like emojis and symbols that aren't like classical text. So they're just basically flags that tell your computer there's something special going on in the text. And the escape character for a new line looks like this. It's like a \n. And so this will split the input text into these different lines. So if the input is multiple lines, then it'll split it like that. And so we first want to split our input text into these multiple lines. And so we're going to get the text from here and split it into these lines. So this will give us a list of lines. And we can check this by going to we'll do this. And then we'll just set this to global input. And let's try this. Okay, so I'm going to get this. Wait, that's the wrong copy. Let me try that. And let's see what we get. Right, so now what we get is this this list with all the different lines split up into these different items in the list. So that's working as intended, and there's 4 lines with 4. We have 4 that tells us there's 4 lines, and we see 4 lines on there, which is good. And so now that we've gotten that, we actually want the input to be, remember, a list of lists. And so we're going to need to split each one of these. And so we can do that by going through each item with a loop. And so we're going to go through each line in this. So this is the list of lines we're going to go through for each line. We're going to add to the list. We're going to add to our input list, the list of words. And so we're going to add item to list. We're going to get the input. And so we're going to add the item that's the split version of the line. Okay, so now if we try this, I don't know if the input stays the same. It does, nice. So now we have in our list, a list of lists, and each list inside the big list is a list of words, which is split from the input. Now, we almost have what we want with this. The one thing is this for. We don't need this for because we don't need to count. We can kind of automatically count the number of lines in this thing. So we can just remove that and get rid of it. And then remove list index 1. So we start at 1 for App Inventor. And if we try this again, our list, the input doesn't have that number that we don't want. So now we just have the sentences that we need in order to solve the problem. Okay, so now looking back at our framework for how we're going to solve this. So we finished the input part. Now we're going to go through each line of input and figure out the next cow's birth year based on that. So we're going to go to solve. And I'm going to use one of these control things because we're going to do something and then the result's going to be something at the end. And we can just do the result part first. Actually, it might be better to test out a few things in between. We can just print result being, for debugging purposes, we'll just print the dictionary, the Cowborn dictionary. So if we do this right now, we're going to get 0 because that's, we're going to get Bessie 0 because that's what we set Bessie to be. And so far that's correct. Now, well, what our control loop looked like in our algorithm was to go through each line of input and compute the next cow's birth year based on the last cow's birth year. Yeah, okay. So we can go through here. Yeah, the reason I'm printing this stuff out to do debugging is also like for other programming languages, print debugging is pretty useful, especially if you don't have like a good debugger. Like a lot of languages don't have a great debugger. And so printing stuff out is very useful, although a little bit jank, but it is good to do so, like print out your outputs when like in the middle of while you're working. So now we're going to go through each line of input and figure out exactly what year the cow is born. Okay, so the very outer layer of our algorithm is to go through every item, every sentence in the list, right? So this is our sentence, let's say, And the list is the global input list. Okay. Now we're going to compute the next cow's birth year. And in order to make things simple, I'm just going to say new next cow. So this is going to be the year for the next cow. And it's going to, at first, we're going to set it to the year of the last cow, because that's the year we're going to base it on. We're going to go to the year of the last cow, and we're going to either count up or count down based on what the sentence says, if it's previous or next. So first we're going to go get that and get the value for key in dictionary. This dictionary is going to be okay, and this well, which key are we going to get? Well, we want the birth year of the last cow in the sentence. And if we look at this, which index are we going to get the key from? So this is 1, 2, 3, 4, 5, 6, 7, 8, right? So we're going to look at the 8th value in our sentence, and that's going to be the name of the cow. That's going to be the name of the cow. So we're going to select list item. This list is going to be the sentence. And we're going to get the 8th item. Right. So this is going to be the 8th. Yeah. This is going to be the name of the last cow that we know. And so next we can look at the sentence itself, and we have to decide whether or not we're counting up or counting down. So that's going to be determined by this word previous, or it's going to be next. So we want to compare this value, this word, to previous and next to figure out whether we're counting up or down. And so we're going to go here because there's two options. One of them is it's previous, or the other one is it's next. And that's going to give us our two options for which one to pick. And so we're going to compare. We're going to check if the word is previous or not. And so which word is going to be in the sentence? Well, we can count through here. 1, 2, 3, 4. And so we're going to get the 4th word of the sentence. And this is going to be either previous or next. And we want to compare this to previous. All right. Okay. So then once we do that, if it is previous, we want to count down until this matches the year matches the dragon, or like monkey or ox, so the animal name. And so, well, first we need to start counting down, but before that, there's like an edge case that you need to think about. So what if I'm already in, let's say Bessie is in the ox year, right? And we want the next cow, and the sentence says, let's say Mildred is in the next ox year from Bessie. So if we just do a loop, or like if we just check right away whether or not they're in the right year or not, then it's just going to spit out the same year. So if the year 0 is the ox year and we want the next ox year, if we do the check right away of is it the right year, right animal year, then it's just going to spit out year 0, which is not true, because the next ox year is year 12. So we want to do this. We want to make sure that we're actually above or below the year. And so we can do we can use a do while, which or we can just kind of, I guess not a do while, they don't have that, but we can make sure to add or subtract 1 to the year first before checking whether it's the right year. Okay, so I'm going to set this to, we're going to first subtract 1 to make sure that we're below. We're going to get minus 1. So now we make sure that we're below the last cow's year. And then we're going to keep checking whether or not it's the right animal. So, well, how do we check if it's the right animal? This is where the modulo comes in. So if I divide the birth year by 12, if we divide the birth year by 12 and then compute the remainder, we can check whether or not it's going to be in the right year, given our dictionary that we defined for all the animals and the remainders. So in order to do that, we need to check if they're equal or not. So while it's not in the right year, is what we're going to do here. While it's not in the right year, we're going to keep subtracting. So this is going to be our next block. It's going to be in here. And then now we need to check if it's the right year or not. And so we compute the modulo, which is modulo this. And we're going to get the cow year and divide by 12. Right. So this is going to be the it will sort the year into one of the classes for the different animals. And while this is not equal to, and we want to check if it's this animal or not. So how do we get the class or the number that defines the modulo for this animal? Well, we can access it from our dictionary. So we're going to get value for key. And this is going to be the 1, 2, 3, 4, 5th word in the sentence. In the dictionary, animal dict. So this is the name of the animal. So for example, dragon, and it's going to go into this dict. It's going to look at dragon and it's going to say the value is 3, and it's going to give it out. It's going to spit that out here. And while the remainder of the next cow's year divided by 12 is not 3, it's going to print out. It's going to print out, or it's going to keep subtracting 1. Okay. So the other case for this, well, we're finished with this case now. Then other case for this is the opposite. We want to keep adding 1. So we can copy this, but this will have to be an add 1. And then we're going to copy this as well. And this. Right. So this will kind of do the same thing as before. It's going to keep adding. If it says next some animal year, it's going to keep adding until it gets up to the right year. So after this block is done, we've actually computed this correct year in this set next cow year. We can now set a value for this. Okay, and then we'll put that here. And we want to set the year for the cow we've just computed, which is this first one, right? So this loop has just done all of this work for the cow Mildred, and we want to make sure we preserve Mildred's birth year. And so put this in here. And then we're going to set the answer to this. Get next cow year. Actually, this is not right. No. So Mildred, in order to get that text, we need to get from the sentence. Yeah, and we're going to get the first word, which is the name of the next cow. Okay, so this kind of looks pretty much the complete thing we finished, and we'll see this. Okay, so now if we look at this, we can kind of confirm basically what the we can try and confirm whether or not this is correct. So first we know Bessie's year is 0, and then the previous dragon year from the ox year, I guess, is -9. And then, so Mildred in the previous monkey year is Greta, so we keep going down to -17. Then Elsie is the next ox year from Greta, so it kept counting up until it reached the next ox year. And then Paulina is the next dog year from Bessie, which is counting up from Bessie, which is 9, I guess. Okay, that looks somewhat right. So now we can just try and computing the answer. And so what was the answer? It was the difference in years between Bessie and Elsie. So what we want is an absolute value, because we don't want negative differences, an absolute value of subtract, and this will be this. And we want Bessie first. And then we want Elsie. Right. So now we can try this out. And you'll see, gets us the answer 12, which is the right answer for this. Right. And this basically confirms what we had before. What we had in our dictionary before. Okay, so now we can, the way these contests usually work is, well, this is like the sample input. Usually what you'll do is they'll give you the sample input and one example solution, and then you'll like kind of put this into your program to see that your program's correct. If it's correct, then you submit it into like their judging system, and it will use bigger test sets, bigger test input, and like more edge cases, like little things that you might not have thought of, and then it will test it against that. And if you can get the right answer in like a designated amount of time and with a designated amount of space, then you pass those cases. Okay, instead of storing animals and modular numbers in a dictionary, could you just store animals in a list and access the index? You could. That's definitely a way you can do it. It's more intuitive, I guess, because you don't actually access the index of, you don't access the list by index, you access it by name. And I can get into a little bit of how this is not actually a terrible trade-off. Like this way of storing it. The list is like slightly better in space complex, or like it's slightly less space, but the time is pretty much the same and it's just more intuitive. So I can get into a little bit of that later, but yeah, you can definitely do that. You just have to figure out the right index based on the name of the animal. I don't get why we use functions when we can just use the blocks in each. You can. Function just another copy paste. That's true, but that's like kind of a very low level way to look at it. Like if you really want to think about it, all code is just copy paste of ones and zeros. But you would like it to be in text because it makes sense to you easier. And that's the point of functions, is to break things down so that it makes sense to you easier, and you don't have to worry about like the whole control flow, right? Like if I have this massive function with all these different things, like just one big chunk of code, well, if something's gone wrong, then I don't know exactly which part it's gone wrong in. If I break it up into functions now, I can just look at these different parts and do parts at a time. Just makes it easier for you to think. If you want to do all your code in the future and now in one big block, there's no one stopping you from doing that. But I'm sure if people want to read your code or you want to read your own code later, it will be much easier if you're splitting them up into functions. Okay, so now we can go through a little bit of these extra test cases. So for example, like this last one was 4 lines of things, and like this is one of the, since this contest is done, this is one of the test cases that they had. And as you can see, it is clearly more than 4 lines. So you have to be able to get all of these lines. So we're just going to copy paste this. And let's go in here. I'm going to make this easier on myself. Okay, so if we solve this, get 31, and we can go in here and check the answer, which is 31, right? And you can go through all of these different parts in order to do that. Yeah, so the solution works. It works pretty fast too. And just for a little, since I have like a little bit of time left, I'm going to go over what we like this time and space complexity of this, because I guess it's nice to go over it. The most common notation that we use, or like I'm going to introduce some notation, which is big O notation. And this is going to be some function f inside this O brackets, and it's going to say this this function is in the same class of complexity as f. Now, what does this mean? Let's say I have a program with a for loop, right? For, and it's going to our input is going to be some number n, and it's going to be for like 1 to n, I'm going to do something. And this do something should be pretty easy, should be very simple, right? So how does the amount of time this program takes scale with the number n? So if n is like 1, then I have a 1 loop, right? But if n is like 100, I have 100 loops. And then, or 100 iterations, I guess. And so the complexity of this program scales with n, and this would be an O of n program. Now, if I have some input n, and I have something like a loop like this, and I have a loop inside of it, and now let's do something. Well, how many iterations do I have? So if n is 1, then I have 1 outer loop and 1 inner loop. And for each outer loop, it'll do the inner loop. So I have 1 times 1, which is 1 iteration. Well, what if n is 10? Well, the outer loop goes 10 times, and the inner loop goes 10 times for each outer loop. So it's going to go 10 times 10, which is 100 iterations. So how does this scale? Well, this is n squared, right? So O of n squared. Now, what will really be the case, like since timing a function is very difficult to do because there's always these little constants, like sometimes addition will take a little longer, and then, or like the number of times you do something will affect it. But what really matters to us is how big, or like how it scales with how big the input is. So like if n gets bigger, it will eventually outweigh any kind of constant things that we have. So like if we say that, well, so one function takes 2n time based on the input n, and another function takes n squared time, or even let's say 100n. Well, if we look at this graph, if we look at the graph of this, well, this is like time, and this is n. 2n squared will go like this, right? And 100n will kind of just go straight up like that. So there is a period of time underneath 100 where 100n is slower. But if you go all the way to the out here to n as it approaches like very, very large numbers, n squared is much, much bigger than 100n. So that's kind of how these different classes work out. And 100, so when you're writing a program and you want speed, the larger the function is inside that O of something, will be the slower it is. And each function in there is kind of is the same class of function. So if we have 100n, this is the same class of function as 2 of n, or 2n. And n squared is the same class of function as 3n squared. They're all equivalent under big O notation. Okay, does that make sense to everyone? Okay, great. And now let's look at the program we just wrote. If we look at one of the great ways to judge this is just look at how many loops we have, and we have one loop which is based on the number of lines in this thing. So and we have these two loops, but these two loops are bounded by 12, right? Because we can only go up, at most we can go up 12. So it's kind of bounded by a very small number, and we know exactly what number it is. It's not based on the input, so it doesn't affect our O of n analysis, our big O analysis. And so for each sentence, this is what concerns us for each sentence. And the number of sentences is the n in the input, or it will determine how slow our program is. So since we have one for each sentence, we have an O of n program. And in general, you want something that's like just as low as possible, but linear, or so linear where it's O of n is good. If you go up to like O of n squared, not as good. And then anything past that is not good for competitive programming things. Yeah, and to kind of go through something kind of a extra little bit, dictionaries actually have constant time access and constant time writing because of the way they're implemented, which is kind of cool. You can go into that, like look into hash maps, but it's very fast to access dictionaries and very fast to write from dictionaries. So you'll never really have to worry about list versus dictionary, which one's faster. Like both of them, whichever one makes the most sense to you, they're both equally as fast for most competitive programming purposes. I think dictionaries are like, the way they're optimized is like very slightly more memory, because it's a basically a big list that you can search through quickly, is the way dictionaries are fast. But the space, it won't matter as much for competitive programming. Okay, yeah, so that was the whole problem and the solution. And I hope you guys learned something from that. And I'll pass it back on to Dr. Ming if he's here. He wanted to wrap up, so yeah. Or if you guys have any other questions, you can just ask.
Okay, thank you very much. Excellent presentation. So thank you very much, Derek. And I think everyone